think we're ready to go, yeah? Okay, welcome back, everybody. So before I launch into the technical part, let me just make sure, so the piece that was released this morning, but I want to make sure you're also thinking about the looming project proposal first draft, and just say a few words about that, right? So some of you have already been working on teaming. Thank you for those of you that are already thinking about that or thinking about your projects. Feel free to be reaching out to us now if you have ideas. The goal for the first draft is for you to put together a somewhat well-formed idea, but that will be, it's fair to sort of say, is this a good project? I mean, we're going to give you feedback on the first draft, expecting that you might, have picked something too big, picked up something too small, and our goal is to help you on that with the first draft. Ideally, you will have your teams locked in for the first draft, and we're just optimizing your proposal and discussing it with you, and that's our best chance to give you direct feedback on the written part. If a little bit of team shuffling happened because of changes in the direction or something from the first draft, that would be okay. But really, ideally, before that first draft, you will have your teams locked in and a pretty good idea of what you want to do. Feel free to reach out to us now. The 6-800 folks are going to get feedback in two forms. They'll get the technical feedback from the three of us, and then you'll get the writing feedback from the CIM staff. The grad students will get just our feedback. And I think this will be clear on the submissions, but the 6-800 folks are going to submit on Canvas, and the 843 will submit on Gradescope. So I'm excited to see what you come up with. The projects are always like the best part of class for me. I just get to see, and I get to learn, honestly. I get, a lot of these questions, like we said one about teaser the other day. I just don't know how well it works on manipulation problems where the points might be arbitrarily small. That was just one example, but I get to figure things out by watching you guys try and tell me what worked and what didn't work. So pick good projects so we can learn a lot. Good, so let me make sure that we're starting the next piece of the class, which I've called in various places either manipulation and clutter or bin picking, because that's the specific instantiation of it we'll think about. But let me just make sure the roadmap so far is clear. So, we started with a quick discussion of the hardware basics, but then the way I want you to think about rolling out the capabilities that you have, right? So you're getting more and more functional in your manipulation tools. First thing we did is we assumed perception was given. We just knew where the object was, and we talked all about kinematics and how to do a basic controller to just reach out and grab it, move something from point A to point B. Okay. Last time, the last section was removing that assumption of perception, and we're going to start at least from depth, reasoning about pose estimation, find that known object in the scene. But that was just a beginning sort of view of what the perception problem is. Okay. So what we're going to do now is we're going to continue to make that more and more rich. Our tools are going to be more and more robust. We're going to start thinking about more complex scenes. Now we'll have many objects, which brings its own problems, and more diverse objects. So our tools are going to have to deal with the diversity of the objects. This will lead us into the deep perception tools in one of the upcoming lectures. But first, we're even just going to be thinking about how do we deal with all these objects? What does it do to our geometric perception, for instance? And in general, we'll try to keep now the perception and control as both topics in the class. We will no longer assume perception is handed to us. In this first wave, even though the scenes are getting complex, we're still doing what I would consider to be relatively simple manipulation, kind of pick and place. So we want to locate and compute geometrically where I can get in and make a good grasp and move it to point A to point B. I made the point in the first lecture that manipulation is more than pick and place, right? So when I'm loading the dishwasher, I don't move like that, right? I have much more. I have in-hand reorientation. I might be bumping up against things to let things slide in my hand because I made intentional contact. There's all these things we're going to get to, but not yet. First, we're going to stick with, we're going to get it from point A to point B, but the scene is complicated. And we'll just keep leveling up. So I think as we start the conversation about more complicated environments, I think one of the first obvious, natural questions would be, how do you simulate or test in your robot, all the random environments that you want to use? So this is work from Greg. He's done sort of random sinks inspired by the dish loading examples, but also random kind of kitchen type environments. And he's looked into probabilistic languages for generating diverse environments in simulation, maybe that can be calibrated to the real world. We'll get back to that if we can in one of in the more advanced lectures. But my point for today is actually this is super hard, right? In general, I'd say that's super hard. People, if you're autonomous, I'm going to switch slides just because that's going to distract people. But if you're like an autonomous driving company, for instance, right? The cache of value that you have is the number of miles you've driven in the real world, and the number of times you've taken, someone that, and it took the real world data and turned that into like a simulation scenario. Like the number of scenarios you've had of random things that happen in the world is like your treasure chest of experience that you have, and whoever has bigger treasure chest, it feels like they're doing really well, right? The same thing would be kind of true in manipulation, but we haven't had the same scale of effort, right? We haven't had people like auto-labeling or manually labeling kitchens yet. Maybe that's next year. But so far, there are shortcuts that people are using in manipulation, simpler instances of the problem where you can generate random scenes sort of simply. They're still very useful for feeding some of the pipelines we want to feed. Right? When we're training deep learning systems, we want to have lots of examples of images that are relevant and lots of examples of robots picking up random things. And you don't need it to be an elaborate kitchen to make that true. You can just dump a lot of things in a bin, for instance. That's what we're going to start with. Okay, but it's a sliver of the much bigger problem of trying to actually parameterize the whole world, right? Or writing a distribution over all possible worlds, right? Not in a multiverse kind of way, but in a what could I possibly see if I wanted a robot to work in everybody's kitchen kind of way. So here's an example, actually very early on at TRI, one of the ways we started, we said we want to start feeding our machine learning hungry algorithms with data, and lots of people have done variants of this. This is just TRI's version of it. We call it the clutter clearing task. And it was a very useful thing to get up off the ground, where we basically can pour any object in the bin and watch the robot pick it up and put it in the other bin kind of all day long. And it's great because you can have important visitors. You say, "Oh, put your wallet in there," and maybe you give it back, right? But but this is this robot really does run all day long for a long time. Collecting lots of data, lots of grasps. It's a super useful pipeline to have. Okay, so let's make sure we can do that kind of pipeline. It is funny because there are some weird objects that get put, so it just became, throw any random object that's roughly the size of the gripper in there. It doesn't matter if it's soft or hard. This thing will just kind of pick it up. And people would throw the weirdest things in there. And then every once in a while, the robot, after running for 8 hours or something, you'd look at it, it had thrown some of them out. And someone found this like rubber duck that looked like Spock. Have you ever seen this? It's like kind of like a rubber duck and it always threw that one out. As far as I could tell, it was like always reject the Spock duck. Okay. So one of the things that happens as we start simulating, working in simulation on these more complicated scenes, is that we have to get more advanced with our simulation, okay? And simulation of complex scenes can be a pretty complicated thing. So to start, we'll just be talking about, how do you populate a bin with lots of random objects? And the simplest version of that is just, drop a bunch of objects out of the sky, and you'll get a random set of configurations every time, start picking them and moving them to the other bin, okay? Now, it's pretty interesting to think about, and we will, I think by the end of the lecture, hopefully understand pretty well why that is the choice that people make in order to make these random bins of clutter, but it's pretty subtle. It doesn't have to be red bricks, although you know I love the little foam red brick. You know, one of the classic data sets that people use in manipulation of just random sort of household objects is the YCB, which is the Yale, Cal, so Yale, Berkeley, and CMU. I always think of that in the wrong way, but it's, yeah, it was CMU at the time, right? And so this is the data set. You'll see like an unusually large number of spam cans and mustard bottles and sugar boxes in manipulation papers, and this is why. It's because there was a project early on to say, let's take some things you can order on Amazon, we'll scan them once in high fidelity, we'll give you good CAD models, and we'll give you rough inertial properties, right? And we'll distribute them to the world, and even say, if you write us a nice letter, we'll send you those the parts, right? So everybody can have the same data and play with the same data in the different labs. Now, unfortunately, like Cheez-It, as a company, didn't comply, right? So now you buy a Cheez-It box at the store with the same SKU, and it says like low carb on it, and so it's like your images are broken, but it's roughly the same, right? And the sugar boxes tend to leak sugar all over the lab, and then the mice come, but it's been pretty darn good to the field. There's a lot of other data sets out there that you might know about or have used if you work on computer vision, but not all of them, a lot of them you would think you would want to use, don't have enough information to be simulated in a manipulation context. So a lot of object data sets that are good enough for visual rendering don't have inertial properties or friction properties or other things. So you have to do some work to either make some assumptions or whatever. This is a data set that with a little bit of work can be good enough for simulation too. So it's been a bedrock. And you can drop random boxes and mustard bottles and spam cans from the sky, and I said it in the notes too. It always cracks me up that you can sort of like see the central limit theorem, even if it's like spam cans and mustard bottles and Campbell soup, right? But if you just drop them, they fall into this canonical distributions, right? Okay, and what's that going to do for us down the line? So we're going to make a grasping system that will reach into this and pick up any box and move it to the next side. You could imagine asking the question, should I estimate the pose of each box one at a time with ICP, with iterative closest point, ICP? And you could potentially, but we'll take a different approach that's going to be more robust and not assume as much about the known objects. So we'll explore that too. But when you start taking overhead pictures like this is the stuff that we're going to, next week, start feeding into our machine learning pipeline. So if I can simulate images, diverse images of cluttered sinks, and I can, in simulation, make ground truth labels saying this pixel is associated with a Domino's sugar, and this one's associated with a Cheez-It, then that's the perfect cache of training data for training a machine learning system. Okay, so that was a little bit about the motivation for why we're going to generate cluttered scenes. But because the ask on the simulator has gone up significantly, and because I think it's important and I like it, we're going to talk about simulating contact. Okay, and my promise to you here is that I hope you will level up your use of simulation. Some people in your questions or comments or PSET have asked questions like, should I have had a physics course recently before I take this class? Is that sort of a prerequisite? We'll talk about equations of motion again here. But I do hope that you don't feel like it's a prerequisite. I think it's important to me, actually, that I think a skill as a roboticist is to be able to abstract a little bit, right? So roboticists sort of have to be the jack of all trades. And I think there is a skill, like it really is a skill you will develop, continue to develop, of getting the gist of something, right? And knowing that you can dig down and having the ability to dig down for details if and when you want. So for those of you that know something about multi-body dynamics, I hope you'll get a lot out of this. For those of you that feel less comfortable. I hope you still get a bunch out of it and know where to dig in a little bit farther if it's not, if it doesn't all land immediately. Okay, and then we'll end talking about some of the things I promised last time about static equilibrium. I think even if you don't love every equation I write, I think you will still become a more proficient user of simulation and at least understand why sometimes simulation blows up. Okay, why is simulation hard for robotics, especially manipulation? Okay. I would contrast this with simulating a quadrotor or simulating an autonomous vehicle, most autonomous vehicles, or a lot of different robots that don't make and break contact with the world as an integral part of their operation. Those tend to be much easier to simulate, okay? But when you start simulating contact, then things get a lot more difficult, okay? Right? In all of the cases, the equations are still F equals ma, right? So there's nothing different about that set of equations for manipulation. So what makes simulating contact more difficult? There's, two basic points that I'll make. I think one of the major reasons is that we get stiff differential equations. Okay, and technically they're even differential inclusions, but I think even this idea of getting stiff equations, I'll make sure you understand what I mean by that. And the fact that the computational geometry gets very complicated and potentially fragile. Our sources of instability, of difficulty that are not present if you're, a quadrotor flying through space without making contact. Okay, so what do I mean by stiff differential equations? I'll come over here and start fresh. Fundamentally, we have equations that look like F equals ma, and we need to integrate them numerically, right? So fundamentally, we're doing numerical integration of equations. So let me take a very overly simple sort of idea where I'm really just integrating a function, and there's no feedback or anything. So imagine I have some function f of t, and I want to take an integral, right? I want to figure out what is x at time t, which would be the integral from 0 to t of f of t prime dt prime plus whatever x of 0 was, right? And how do I go about doing that? Like, just thinking about what you already know about integration. Maybe you've used this to derive the basic rules of integration, but certainly people use them in numerical integration too, is that you end up breaking up the problem into a series of discrete evaluations of your function, right? And then taking coarse approximations of your function, right? That would be a trapezoidal type approximation, right? And you integrate all the pieces, right? And if you're saying something about calculus, you take a limit as those intervals go to 0. But if you're writing an algorithm, they don't go to 0. They stay. There's some finite discretization that has to happen in your solver in order to make progress. Okay. So, and there's various ways. We have the trapezoidal rules, right, to do this. You can also take higher order integration, right? So you can evaluate more times inside each region and make a more advanced approximation. But still taking, of course, time steps. There's lots that's known about that in the numerical integration. So what are the cases that make that hard, right? So if I had a different function here that did something like this, okay, right? And I'm happily marching along, and I take my random integration intervals, and I'm approximating it with my segments here, and I just got a little unlucky and had to go like that, right? You can get potentially very big errors in your integral if your function changes very quickly, right? So this would be, f of t changing quickly. And what does it imply? It implies that you're going to need to take very small time steps, right? So if this is time, this is my time step here. Implies to get accurate solutions, you need delta t to be small. Right? At some point, if I make them small enough, I can get a good accurate integration. But this one, as I've drawn it, is actually particularly frustrating, right? Because you don't need small delta t everywhere. You only just need it right there, right? So it's kind of a waste of energy to take a constant delta t and just simulate slowly all the time, because that gets expensive, and that's when simulators get slow, is that they're taking these really small time steps, right? All because there's a fear of a possible event like this, okay? But that happens, right? So this is one of the ways that someone would call it a stiff differential equation, when you have a difference in time scales, or something that makes your time scale need to be very, very small. That would be considered a stiff differential equation. When this was a x dot, it's a differential equation, right? There are other, stiff is a kind of overloaded word. People use it for when some variables have big time steps and others are change fast. Okay, but this is fundamentally what's happening in contact. And I think that's not totally surprising that you could be, moving along suddenly and you make contact and you get these big jumps, but we'll try to understand a little bit more deeply why that's happening and how people are addressing it. Okay, so contact leads to these stiff differential equations. Now it's interesting to think, so if you've thought about numerical integration before, there's actually a lot of tools to potentially address those kind of problems, right? If you're in MATLAB and you've got a suite of integrators to choose from, and you think, okay, I've got a system that does this, well, there's a bunch of things I could try to do, right? So one of them would be variable step integration. Also known as error controlled. And the basic ideas there would be you try to take big time steps, but you take a couple different, you try to take different integrations. So maybe I'll use a fourth order update and a fifth order update, both in my big steps. And if they match, I feel like I've got confidence that I've chosen a safe step. If they give very different results with two different integration schemes, then you think, oh, I missed something. I need to reduce my time step, right? And these can have the property that they can take big time steps here and then possibly take small time steps here. And they can work for robotics. Not many simulators use them because it's kind of annoying. Like if you want your simulation to play at real time, for instance, right? This is going to have something that is fast sometimes and then slow during the interesting parts and then fast again. So it's not as popular for that reason. Certainly game engines don't use that. Game engines want to have a locked time step and do this. We do have a whole integration suite in Drake to do that kind of stuff. And we actually, when we're debugging our fixed time step algorithms, which we also like, but we like the ability to run the error-controlled integration to check that we get the right answer, even if it runs slow, and then it can use it as unit tests against our faster solvers. there's another idea there too, which is to do explicit event detection. Okay, where you might actually, if this is a contact happening, you might actually tell your simulator about the existence of these events, right? And say, look for the distance between my objects crossing 0. If you know about zero crossing detection, right? And you can sometimes do more to sort of tell your simulators about that. But in addition to being potentially slow, and this being great, in fact, for my walking robots, we did a lot of event detection and we simulated very well, and we're very happy with that. But in manipulation, it doesn't scale, right? If I have a robot foot that hits the ground every once in a while, I can register every event and be very happy with that. If I'm a dexterous hand grabbing a mug and I've got like a million events happening in one grasp, it just doesn't work. So we traditionally haven't used event detection in manipulation. Okay, so what do people do? There's a lot of good work in the simulator world for multi-body simulation of basically trying to figure out how to make these approximations robust, if not correct. We don't actually know. Well, a lot of them that we're using a lot, we don't actually have any guarantees that they're correct. Some of them might add energy into the system. There's some problems with some of them, okay? But we try to take big time steps, and we think a lot about the integration scheme that we use inside there, often to the point where we are solving a small optimization problem to make the best, the best update we can over a finite interval, okay? And this has allowed people to take big time steps again and have performance simulators, okay? So, more advanced integration, and they often lead to these time stepping methods. One of the most famous is they're called solving linear complementarity problems, LCP. That's the name of the optimization solved at each step. And these don't call, Mosek or Gurobi or Snopt. They're calling highly specialized solvers that are tuned in exactly for the multi-body equations. They use as much as they can about the sparsity, and they have to be specialized in order to be effective. Okay, and still, I heard a great talk yesterday about a new integration scheme for these kind of methods. This is continued to be active research, and it can be a game changer for the field if someone makes progress in that. Okay, so I'm going to try to tell you, at least the basic ideas behind here, and connect it to the physics, right? So I want you to have an intuition of from the physical equations, why do these jumps happen? What can we do about them? And I want you to come away with a practical understanding, like if my simulator looks like, my objects look like they're Mexican jumping beans, what do I do about it? Or if my Atlas used to explode, right? So like we'd be working on our Atlas in simulation and it would literally explode, and that would be frustrating when you're working on a controller, and sometimes it was our fault and sometimes it was the simulator's fault. But you should come away from this with an increased understanding of what you would do about it and why that sometimes happens. All right, so let's think about some of the basic physics of contact. I'm happy to take any questions about that too, if people have any questions. Okay, let's say I've got a sphere, mass m. You're going to do this a bit on your PSET too. Gravity's down, okay? I've got a ground plane. What does the sphere do? Okay, so it's going to come down. Now, the natural thing to say is that's a ball that would bounce, but in our class, spheres don't bounce. We have, In manipulation, you mostly don't want things to be bouncing around. And in practice, a lot of things you're picking up, you pick them up with a padded finger or something like this. But you could certainly expect it to bounce if there's some elasticity, right? If there's an elastic contact. The coefficient of restitution is what we talk about, but we drive it to 0. Okay, we say, here we're going to do inelastic. We can get back to elastic. It's not that we can't simulate. Elastic is just, I think the exposition is cleaner if we just let it go funk. Okay, for now, right? So that's an assumption. It's like elasticity 0. So the ball's going to go down, hit the ground and stop. Okay, but it's actually really subtle how it happens, right? And it has all those issues, right? So the equations of motion here are simple, right? I can call it Q, or I'll call it Z, I guess, if just my Z height here of the ball. It's just F equals ma, right? So it's just going to be negative G, mg, sorry. Right? And when it's in the air, that's all that's happening, okay? When we hit the ground, when we get to the second configuration, oops, let me make it exactly kiss the ground here for this, okay? There's going to be a new force involved, which is going to be our contact force. We're going to have various notation to talk about spatial forces, right? So if you remember, we did spatial velocities already, and accelerations, where we said the big V we could have all the stuff. It's got a rotational component and a translational component, right? And we're going to have spatial forces too, where I'll have a big F. Let's just say I'm going to have the translational torques, okay, and I'll have the small f be my horizontal, or my translational velocities, okay? They can have A relative to B, all this stuff. They don't always need all that, but it's available, okay? And in particular, we're going to typically work in a coordinate frame that's called the contact frame, which will be right here. Okay, so that's just a long way of me saying I want to call that force, the force on, let's say, body, I'll call it force on M in the contact frame. And since my contact frame, I'm going to always say that the normal is the Z component. It's the Z component, okay? It'll save us later, but I know it feels heavy right now. It's always sometimes, it's also called the normal force. And I'll sometimes in the notes, I actually I almost always write this, and I long to get myself to really write this all the time. So I sometimes just write the normal force like that. Yeah?
Could you write a little bigger?
Sounds good, yeah. The request was to write bigger. I'm sure the people watching online think that too. So, if there's anything you need me to rewrite, I'm happy to, but otherwise I'll be bigger going forward. Yeah. Okay, so when we're in the contact configuration, we get this additional component here. It happens that everything's in the same frame. So it's going to be in the world Z here. on mass is what I care about here, but it happens that C and W are aligned in this case. Okay, so what do we expect the trajectory of the ball to look like? Okay, so if I have time here, maybe I need to, I start with an initial Z. Let me even, it's even simpler to think about Z dot first. Let's think about Z dot. Let's say it starts at 0. Okay, before contact, let's say that my time of contact happens over here. Time of contact. Before contact, I just have this linear acceleration. Constant acceleration, which means a linear velocity. Right? Now, at the moment of contact, I have a decision to make. Okay, I have, you know, there's a couple different, there's only really 2 different ways I'd say to talk about what F should be. Okay, but the pure version that I think you kind of like mathematically would be to say, I never penetrate the ground, right? That force does whatever it needs to do in order to prevent me from penetrating the ground. That's sort of a natural definition. But in order for that to be true, if I'm coming down with a positive z velocity, and then all of a sudden, at this instant that I hit the ground, my z velocity has to instantaneously become 0. Otherwise, I will penetrate the ground. That means that I have a discontinuous jump at the moment I hit the ground. Okay? So that is what we'll call the rigid what people call the rigid contact model. Say, how do I solve for the force? Call it on force on M. Option 1 is, I would say, the rigid contact approach. So you actually solve a small optimization problem potentially in the harder cases, and you try to compute what is the smallest force possible that could avoid penetration. So this becomes a constrained optimization. I could write it as there's some constraint where z has got to be greater than or equal to 0 for all time, and the force ends up being whatever it needs to be in order to make z greater than or equal to 0. But among all the forces that could keep z from going less than 0, it's the smallest one. That's called the principle of least action. Comes from the principle of least action. Okay, so that's a well-defined problem, right? I can figure out You know, I could solve for whatever f needs to be to make sure that z never goes less than 0. Yes?
So if you have to continuously change your velocity, doesn't that make the acceleration infinite?
Good. So yeah, so that was exactly the next question. So the question is, doesn't that mean f has to be infinite? Yes. So in order to do rigid contact, in order for this to happen, where f is going to be 0 in the continuous time until the moment that it hits the ground, and if the velocity changes discontinuously, the acceleration. So the way to think about that is f has to be impulsive. It has to be a delta function, right? It has to have finite results, change in velocity over an infinitesimal instant in time. Right, delta function. It's going to look something like this. There's some delta function sitting there. The moment you make contact, you have an impulsive collision. Now that's not, I mean, so nothing is actually rigid in practice, okay? I mean, even when people run on treadmills, it happens, you know, I worked on walking robots a lot, so people who run on treadmills, if you look at the way you run on treadmills, at the moment of heel strike, you see a big, huge spike, and then you'll see the constant sort of stance force, right? That's a real thing. I mean, you'll see this kind of a pattern on a gait analysis machine, if you're running on a gait analysis machine. Most people don't run on a treadmill with real-time force feedback, but it's cool. Okay, so that's sort of a real thing. Now, the real systems aren't infinitely rigid, so there'll be a little bit of deformation of the objects. So in practice, it's not an impulse, it's a spread out a little bit over time, but it can be very sharp. Okay? And in fact, I think you should really think about this as rigid contact is not reality. It's an approximation we make to reality that can be good for some algorithms and bad for other algorithms. Okay? For some of the trajectory optimization, it actually makes things good because we can do explicit event detection, make a decision variable exactly for that, you know, and then otherwise have simple problems. For simulation, it's typically not. For manipulation simulation, it's not typically done. Okay, does that make sense? This fact that you need an impulse here? So that's potentially bad news for a simulator. If you're not doing event, so I think when you have this, you want to be doing event detection. Otherwise, you're not going to integrate that very carefully. Okay. If, however, in discrete time, if we're willing to do these fixed time step solvers, we can make an approximation. So this, if I wrote this a little bit more carefully, might say z of t greater than or equal to 0 for all possible t. Okay? In discrete time, when we're taking these big time step algorithms, one of the things that we do is we relax that a little bit. We say that, well, z at my dt, as my constant interval of dt, so my, let's say, dt times k, at my kth step has to be greater than or equal to 0. Did I say that well enough? So I plot z, time here, z of t. If I'm making discrete updates, and I'm only looking at it at a fixed dt's, 2 dt, 3 dt, I got small, sorry. Okay? If I only require that z is greater than 0 here, at the finite points, I only implement my constraint at these points, then it's enough to say the total integral of the force over an interval is sufficient to put me into out of penetration. Okay? So that can be finite, again, and that can be well behaved. Does that make sense? Yeah? So basically, so if I hit the ground somewhere in the interval between delta t and 2 delta t, I don't have to potentially do event detection. I have to solve for some force, which when integrated over this interval, will make sure that I'm out of penetration, or exactly on penetration at the end of the interval. That means my force has a finite duration of time to work over and becomes finite again. It removes these delta functions that are nasty. And that's the fundamental idea that happens in these discrete time-stepping solvers. Yeah?
So what happens if you're predicted to hit the ground in between the time steps?
Mm-hmm.
So like I hit at delta t divided by 2.
Yep. So the question is, what happens if you're predicted to hit the time, just between the time steps? So it handles that very well. So it gets, the forces are allowed to be non-zero if at the end of time the constraint needs to be active. That's these semi-implicit methods. So the rules are, at the end of each interval, you must satisfy the constraints. And you're allowed to have force that's non-zero if it's required to make your constraints act, that you stay out of penetration at the end of time. The harder one, actually, is if I'm leaving contact in the middle of an interval, okay, then you must be able to leave contact without force. That's the trade-off that the solvers typically make, okay? But they solve these small problems such that at the end of each interval, you will satisfy those constraints. Yes?
I'm thinking like if you're simulating a robot that has torque limits and you have simulated it at high frequency, don't you get ridiculously large forces?
Okay, so the question is, if I have torque limits, but I simulated a high frequency, can I get arbitrarily large forces? So I think we have to be a little careful there. So I think if the torques are limited at every step, but they are changing very rapidly, and you integrate them badly, then you could imagine adding power into the system and cause things to look aphysical or whatever. But I think that would be, that's not the governing equations that are wrong in that case. That's meaning that you're probably integrating them incorrectly, right? So if you take large, quickly changing torques and you're not integrating carefully, things could lead to high errors. Okay, so this is the rigid contact assumption. And it's gross in this way, but with some time averaged approximations, it can become reasonable again, okay? And the hope is to try to enforce these constraints completely. Option 2 is a soft contact model, or compliant contact. Okay. And in a soft or compliant contact, you no longer try to solve an optimization problem. I mean, there's versions that combine all these ideas, but in the simplest form of soft contact, you actually prescribe that the force is a function. You allow your system to penetrate, two bodies to penetrate a little bit, so the ball's going to go a little bit under the ground, but you make a force that resists, that's proportional, let's say, to this, like a spring pushing you out of the ground. The ground becomes a spring. Okay, so you might have something like your force in the world or in the contact frame equals 0 if z is greater than or equal to 0, or negative kz if z is less than 0. And physically, that might look like the ball actually will go under the ground, and I've got a little tiny spring pushing me back up, producing some force. Okay? More generally, we'll add damping and stuff too. Something like that. These are still discontinuous. Sorry, they're continuous, but they're not differential. Something changes at the moment where you hit the ground, but it's at least continuous, right? In fact, the way that people will plot these, I think the way to think about it here is if I think of z as my function here, the rigid contact model, for all positive z's, the force must be 0. And when z equals 0, it could be anything positive here. For my soft contact model, I'm going to get something that looks more like this. Okay, where this is my stiffness K. Makes a spring law. Okay. In fact, so I made it easy with it's just a ball falling down vertically. So the distance between the ball and the world and the ground is just z. More generally, that distance, we've already seen a name for that distance, right? We've used phi for sine distance function, okay? And actually, sine distance function is exactly what we want to use here, again, for all the contact computations, right? So more generally, this could be phi, which would be a total function of q. All my position variables, which is the sine distance function. Let's say between body A and body B. Okay, so the general version of these plots, they still, in the frame of the contact, phi plays an extremely important role, okay? It's the number, it's a scalar, but it happens to represent, exactly the distance between the objects, and it sort of defines the coordinate system of our contact frame. Okay, so we want where phi is going up to be the z-axis of our contact frame. Okay, and we still make these plots saying that the force in z of our contact frame, it can look like this in the rigid, or like this in the soft. And you can choose different curves if you want to, right? Yeah.
This model has to bounce, though, right?
It doesn't have to bounce if there's dissipation, right? You can, in fact, a lot of times you'll have even an asymmetric dissipation, so that it will, it'll come in and it'll try to resist a lot of energy, like when you're pulling back up. Yeah.
So you decide you have to put in the damping, otherwise you wouldn't bounce.
You would bounce if you didn't have damping. Otherwise, yeah.
So that you don't have.
Yeah. Mm-hmm. And you can simulate soft contact with in continuous time, or discrete time. You can try to do the event detection or not. That really doesn't change, okay? But in particular, so choosing K is a big deal, right? This is one of the things that you should think about when your simulator's not working well, right? Is that where is the stiffness in my problem coming from, right? If k is very large, then I could have a stiff set of differential equations. I'm making my equations more stiff, and I probably have to take smaller time steps, okay? So, how do you pick k? Well, it depends on the inertia in your system, right? So if I'm a 400-pound humanoid and I'm sitting on the ground and I don't want to be 6 feet under the ground, then I need a large k to keep me pushing back up, right? So you have to be careful. I mean, what we really care about is the stiffness and acceleration, right? So you can potentially choose a large k and have an inertial system and still have a reasonable set of accelerations that are not too stiff, which is why walking robots have often worked well and they've been easy to simulate, okay? But if Atlas starts trying to pick up a toothpick or something like this, right? Then you get this huge range of inertias and you have to pick some stiffness to rule them all, right? And that's where things get really bad, right? You get some huge forces to try to keep Atlas out of the ground and you apply it to a little toothpick and things go, right? It really, that does happen, right? And I mean, even, I heard a talk from, we worked a lot on the Atlas simulation, right? And at the end of the simulation, we had done all this work on model-based control, right? And we're thinking about, we take the URDF in, we write a great controller, it's optimal in some ways or whatever. And after the simulation, I hear this talk and they say, we had trouble making the simulator work fast enough. So we realized that if we make the fingers 10 times heavier, then the simulator could run faster. And I'm like, what? I just, I wrote all this math to assume that the fingers were a certain, you can't just change the fingers behind the scenes. I was like, I'm a pretty laid back guy, but I think those pictures, those cartoons where you're it gets red and then steam starts coming out of the ears, because I didn't sleep for 2 years working on that robot and then people are just changing masses behind the scenes. But that's true. I mean, if you have a dexterous hand with little light inertias in your fingers and a big heavy robot, that's the bad case. That's the really bad case for trying to choose these spring constants and trying to make a good simulator. Yeah?
Could you not just pick different spring constants for different things? So in that case, a smaller one for the toothpick and a different one for the ground.
So that's a subtle point, right? So how do you choose these stiffnesses? Do you choose them per body or per pair of bodies, right? Most of the simulators, you pick them per body, and then the stiffness that you get as you interact between two bodies is some combination of those two stiffnesses, right? Really, the true properties would be a function of the material properties, pair of material properties, right? But it becomes very cumbersome to have to, for every possible pair of materials, to specify that. Even then, I think you could have big forces coming from Atlas's feet, interacting with the solver with small forces at the fingers, and things are still very tough in the stiffness of the differential equations sense. Okay. And if you don't do event detection, which I said people really don't, you have to think that the stiffness you choose is not just about the resting depth of the resting penetration at steady state. That stiffness has to do all the work of stopping you when you fall into the ground, that initial contact. It has to do the work of the impulse too. So people think, oh, it's not a big deal. I'm going to just let my robot at steady state go a little bit under the ground. But that's not true, because at impact, you might go way into the ground and not be happy. Right? Okay. So you'll see, actually, if you look at the code, right? So when you call multi-body plant, there's this mysterious time step parameter, right? It defaults to 0, right? So now you know a lot more about what that time step's doing. Okay, so in the Drake systems framework, each individual system can declare what its update rates are, right? You don't have to say use one time step for the entire system. You can say this system, this subsystem must be integrated at this time step. If time step is 0, then it tries to use the continuous time variable step integration and do accurate integration. And it should be stable, but it will be slow. And it will slow down at the contacts, right? It'll It'll take big steps. Your simulator will move fast, and then it'll make contact, and it'll slow down. It'll simulate very carefully, and then it'll speed back up. Okay, but for sanity checking your physics, that's great. That's super useful. Okay, if you then pick, oftentimes we'll pick like 1 kilohertz or something here as 1 millisecond for the time step, right? Or some small numbers like this. If you see your system blowing up, the first thing you should do is figure out what's causing stiffness, right? But you can also turn the time step down and expect it to work better, and then slowly move it back up. Yeah?
I imagine someone has, and what would happen if you made the stiffness change depending on the depth? So instead of just having like a piecewise linear, you made it so as it went deeper, the stiffness increased, and then you'd be able to resist.
Yeah, good. Right, so people will choose different functions for this. Some of them do increase in a nonlinear way as you go deep. Absolutely, that's a good idea. I think, yeah, absolutely a good idea. I only cartoon the linear spring. Yeah. Okay, so we thought a little bit about normal forces and trying to prevent penetration. Let's think about friction. Yeah. I'll come over here. Caveat, rigid body friction has all these weird quirks, right? So it's an imperfect model. You can get yourself in situations where there's no good solution given our models, or there's no unique solution, for instance. So with that caveat, I'll tell you what the common models are, right? Degenerate Solutions. Okay, but despite that, everybody uses it. Okay. So just to think, I've got maybe my ball coming down. It's still plastic. It's still going to stick. But now when it hits the ground, boom, I'm going to have not only a normal force, but I'll have some tangential force. Okay. So in my Z frame, and then I'll have my, let's say, CX, or my, sometimes I'll call this is the normal force. I often use the shorthand Fn, and this is the tangential force. Often shorthand F tangential. The same way that the normal force, sort of the cleanest statement of the problem, sorry, did you have a question? No. Okay. The simplest statement of the question is the normal force is whatever the smallest force it needs to be to resist penetration. The simplest specification of the friction force is it's the force that it needs to be to stop horizontal motion. Okay? So FCX is whatever force is needed to stop horizontal motion. Which is tangential velocity. So that would be the velocity of body A relative to body B at the contact frame, expressed in the contact frame. In let's say X. Contact frame. If I had no limits on friction, this is what it's going to do. You're going to solve for whatever force is needed. Okay. But in practice, friction is limited, so we up to some limit. And the standard model of that is Coulomb friction. Where we say that I'll just write Ft is less than some coefficient of friction times my normal force. The way I've drawn it, my normal force is always positive, but I can do this just to be careful, I guess. So this is a coefficient of friction. It's also, the Coulomb friction is also known, described often as called the friction cone, because that is a conic constraint. You see in 3D on my plot there, in 3D, I still have the normal and I have two tangential velocities, right? I always have this contact frame. Right? In the contact frame, if I have my normal force, then the tangential force is proportional to the normal force. So it comes up like a cone, right? Depending on what my normal force is, if I have more normal force, if I'm pushing down harder on the ground, I can have more friction force proportionally. If I were able to draw that well enough on the screen, if I have, tangential direction 1, tangential direction 2 in my normal direction, then it really does look like a friction cone, because if that's an L2, which it almost always is, an L2, Euclidean distance there, then it really is this cone. Okay? So we call that the friction cone. It's the admissible frictions, which are a function of the normals. Okay, so the definition is pretty simple. It's whatever up to this limit, it's whatever the friction needs to be to match that. And then if you are sliding, if you are not able to produce enough friction to completely stop resist motion, then it will be the maximum dissipation. So it will be whatever force it does that slows you down the most, which is always it's in the direction resisting your velocity. Okay, these are all details, but friction tries to stop you in the tangential velocity, right? Sliding friction tends to be, we tend to have two coefficient of frictions. So let me make sure this plot makes sense here, but the same way I was able to draw the normal force as a function of the sine distance. Here I'm looking at the tangential velocity in the contact frame. That's x here. And the plot that you will see is that when there's zero velocity, when zero velocity is possible, I can have whatever force I'm allowed to have up to the mu static friction, if I distinguish between the two. And once I start sliding, I expect my force to be as big as possible to resist motion, okay? And this would be potentially a different number. Sometimes the dynamics friction and static friction are set the same, but typically you can get more force in stiction than when you're sliding. You get slightly less force. So you'll transition to a maximum dissipation with a slightly smaller limit. And you will see some of the simulators if you don't do this strict optimization sort of to get to impose those exactly, you'll see approximations of this that look like these kind of nonlinear, stiff sort of approximations of that are used in the simulators. One of them that we use in Drake is called the Stribec Approximation. Stribec, German. Now, the same thing you asked about for stiffnesses is true here. the static friction you'd expect and the dynamic friction you expect between two objects is really a function of the material pairs. But in practice, almost all of the simulators, all the URDFs, everything, you specify a coefficient of friction for this object and for this object, and then the simulators do a best effort for every pair to turn it into some averaged coefficient of friction between the two. Okay, so all of these things lead to potential stiffness in the equations, right? The numerical integration story I told you at the beginning, you have all this stuff, like these are all big, ugly functions that are going boom, right? So that's what makes simulating these things hard. And the best solvers, I mean, the good work here is a lot of work at the numerical methods of simulating those equations, efficiently, taking as big steps as you can in the details of how you do, matrix inverses or basic least squares kind of solutions. They're really in the weeds. They're trying to exploit all the sparsity in the equations. It's tough stuff. Okay, it gets worse too. So it gets worse too. I told you there's two big problems, right? There was the stiffness of the equations. The other thing that happens is that the contact geometries are really ugly. Okay, so one of the things that I kind of alluded to here is that a lot of the models allow you to penetrate the ground a little bit, or two objects will penetrate themselves a little bit. Even the rigid models, it turns out that the optimization problems we solve, in order to make them efficient, we tend to linearize. We take Jacobians, for instance, to linearize the friction cones and the constraints. And because that's an approximation, we can actually, even the rigid models do allow some penetration. So you get two bodies that are overlapping. As you will see in your problem set, even computing sign distance functions when things are in overlapping gets ugly, okay? And it's not exactly, you want something that's slightly different than the sign distance inside. You want the maximum penetration depth, okay? But that stuff gets really, really bad. And it's a source of a lot of problems in simulators. So let me just, actually, I had some slides I put together the other day, so let me show you some of the work that we do to try to make that better, but it's hard stuff. Okay, so in walking, this wasn't really a problem for me, right? Like really, point contacts, simple geometries were pretty good, okay? But once you get more, if you get like a coffee mug interacting with a dexterous hand, and they start overlapping, and you think, okay, where are the forces to be applied on these two overlapping bodies? You'll quickly realize, and I actually made a little GUI in the course notes, if you start taking bodies and plot them over each other, you'll realize there's kind of no good answer. If you want to summarize the overlap of two bodies and with a single point force or wrench or something to push it out of contact, out of penetration, it's a bad problem, okay? So if you think about these, like this is a logical choice. It's not the only choice. You could imagine putting it here or here or here. You could, I mean, you probably don't want to put it there, but where should you push the force to push things out of penetration? Okay? This is the way that point contact, if you try to summarize the overlap of two bodies with a single point, as it's implemented in Drake, it makes one set of choices, which is no better or worse than any other. It's the one we chose that was best. It still looks a little weird in this particular configuration, okay? But the problem with it, if you noticed, is that it's going, and then it changes discontinuously, okay? So if you, for almost any rule that you pick of like, how am I going to decide, given instantaneous snapshot of two bodies, which direction I should put the force, if you go into deeper penetration, then that force can change very discontinuously, okay? This is a big reason why simulators blow up. If you get a little bit too much penetration, boom, you just like explode out. Like if my ball's coming down here, all of a sudden it explodes out the side, right? This is a big problem. Partial phi, partial q happens to be the gradients, the normals and stuff, but it's really, that's kind of what it looks like on the inside, and it's messy stuff. So you will see in our simulators, if you were to open up the URDF of the YCB objects, or my little red foam brick, we actually, to make that good and consistent, and to make the forces always appear in the sort of unique, or in the same location stably, we will actually often annotate our geometry with little point spheres, okay? So our box is actually a box collision geometry and 8 sphere geometries of radius almost 0, okay? That way, and when you drop those boxes, there's going to be consistent contact forces between the spheres and the other boxes that are inset just a little bit, and that's what gives you like robust and stable simulations. But it's a total pain, and for all settings, knowing where to put those spheres is like a major pain point. So one of the things we've been working on inside Drake is this generalization of that idea, okay, where we try to, instead of taking one point at a time, most simulators choose a few points with some heuristics, but it leads to instability. We've been trying to just do the harder work, the extra computational geometry, to take an integral over an entire surface between the two bodies. And so we have a very robust and numerically stable contact wrench that comes out of that, forces and torques that comes out of that. So it's moving away from point contact, but it's much less than a full finite. It looks a little bit like a finite element method when I draw it like that, but the geometries and the masses are not changing. This is a rigid shape that stays the same shape all the time, but instantaneously we're just integrating the force more like a limit surface, for those of you that know about limit surfaces, but for 3D geometries. Okay, and you'll see lots of examples of like just some things that were very unstable before become very stable when you just do the extra work of integrating that extra, and it's a lot of extra work, okay? Now, when boxes penetrate, we take an integral and we get beautiful, smooth contact forces, okay? You can make one object hard and one object soft. You can make them both soft, and you get sort of some surface that's like in between the two, all right? And there's just like a lot of computational geometry behind it. Yeah?
So if you had a soft object and a hard object in the real world, and you motion controlled one across the other, wouldn't you get a nearly discontinuous force resulting? Because it would like snap.
So I think the notion of penetration is like a weird limitation of rigid body physics, right? Like actually things are moving out of the way, right? And they're resisting along this surface, right? So how do you take two geometries, assume that, act like their geometries haven't changed, but then kind of produce a force as if the things had moved out of the way? That's the game we end up playing. So if you actually took a rigid object and shoved it to a soft, we'd have to think exactly about how that would work, and the material properties would start to coming into play, right? Yeah. If I took a book and shoved it through a teddy bear, maybe, I don't know. That's probably not what you're thinking, but yeah, I mean, the teddy bear is going to like deform underneath it, right? And it's going to resist in certain ways. This is our proposed approximation of that. Yeah. So when you see some of the more advanced sims, like for the Allegro hand picking up the mug, you'll see some of these like extra renders off to the side here of like the full contact patch being computed. And it just like over and over ago, we've seen simulations that were kind of barely stable or unstable or took a lot of work sprinkling contact spheres all over the place, but give very stable contact forces with the extra work that goes into that. Right, so it's like picking up pieces of potato or whatever we're simulating in this one, right? And you're doing a lot of work to simulate those surfaces, but it's kind of we think it's kind of a Goldilocks between the point contact, which is fast but unstable and inaccurate, and finite elements too expensive. This is like getting just the geometry piece, not all the extra state variables. So we've done things like simulate Legos. You get these beautiful stable matings of Legos. Okay, and when you actually do these sort of experiments of trying to drop things that cross that terrible boundary, okay, and you look at the difference between a point contact model, even in the frictionless cases, the simple thing, versus the hydroelastic model, it just takes a lot of the grossness and gets rid of it. So all of some of the discontinuities that just come from the geometry computations get better. Things that were discontinuous solutions become continuous, right? So there's two major sources of grossness. One is the stiffness of the equations. The other one is, I think, the computational geometry of penetrating bodies, okay? I guess I'll save the static equilibrium since we're running up on time. But if people have questions, I mean, this is a lot of, you know, I hope opening up your awareness of these topics. You don't have to know every detail about all these models. I didn't give you every detail. But I hope you'll come away with like this sense that there's these parameters sitting around in your simulator, right? If you want to simulate faster, you got to make things less stiff, right? And then take bigger time steps. Those two have to play together. When I see people like saying, oh, we chose a time step of 5 milliseconds and we never looked back and we started changing robots and whatever, that just doesn't make sense to me. You have to those two have to be tuned together. You put a different robot in, the first thing you should do is find the right time step for that robot so you can get maximum simulation performance. Yeah?
So this is clearly like an approximation of sort of what goes on in the real world for computational reasons. Is it usually good enough for like manipulation? Like if we do things with these sort of simulation in sim and then try to do it in the real world, are the policies or whatever we figure out robust enough to?
Awesome question. So the question was, there's a lot of approximations in here. Is it good enough? Can we do things in simulation and expect them to transfer to reality, right? So you will see simulators out there that are using these equations, and they can be made very accurate. So let me just say, like Mojoko is a great simulator, but if you are a machine learning person who is trying to make your learning curve look good, you can take these parameters and make them ridiculous and make videos that don't look like physics, and they become easier to optimize and you get a better learning curve. So there are a lot of, I think it's not Mojoko's fault, but people have taken those parameters and made them ridiculous, and then those simulations are not going to transfer to reality. If you take and set these parameters well, then I do think there's a lot of good sim to real work coming on. I mean, over and over again, we're training things in simulation and seeing them work in reality. I think we have spent a lot of time matching those two, and not every simulator has. There are still foibles in these formulations. So maybe one of my favorite ones, if you hang with me for the last minute, but one of the classic examples of where the Coulomb friction model isn't good enough. So if I take a four-legged table, and let's just say it's balancing on the ground. So to say that it's not penetrating, there's 4 contact forces, assuming there's 4 points, okay? 4 contact forces. The sum of those forces has to equal the weight of the table, okay? But the actual balance of the forces need not be uniform. There's really nothing in the don't penetrate the ground that tells me how those forces should be distributed. But the friction depends on the normal force. So if I walk up and shove the table sideways, these rules don't tell me where it's going to go. It could go off to one side, it can go off to the other side. My equations haven't actually told me which of those solutions is real, right? Because I could have put a lot of my normal force on one corner, right? So I get a lot of friction in one corner, it starts spinning. I just haven't, I've written degenerate equations on the board and in our code and in every friction rigid body model everywhere. So that's real. At some point, you have to model the deformation to resolve some of those inefficiencies. Okay, I know we're up against the hour.